now we'll take a look at some simple map implementations. So first off, we'll look at some example problems. And in our example problems, we'll think of this as being a really simple store. The item's name will actually be used as the key rather than the strings we were looking at in the Amazon data. So for example, some of the items we'll include in our store are oranges and light bulbs, and there will be other examples. So those will be the keys that we're using. The value will be data about the item, so it might be price, the number of items in inventory, and other things like that. And we really don't care about that for our examples. We'll ignore the values, and we'll just kind of focus on how we're storing things by key so we can later retrieve them by key. Okay, so our first example will be a map implemented with an unordered list. So this could be a linked list, or it could be an array-based list. So for my example, I'm going to assume that it's a linked list. Okay, so for my example here, I'm going to go through a variety of put operations. So again, I'm just going to focus on the keys, and I'm going to use little cards to kind of indicate what's being put in my unordered list. So imagine first that I put a lemon in my list. And then maybe after that, I put a mouse in my list. Then maybe after that, I put a light bulb in my list. Okay, on the surface, it might seem like my put operation is being done in constant time, but I am actually neglecting something. If you remember, the put operation may update a value. So I'm going to start over again. I'm going to put my lemon in my list. And when I go to put my mouse in my list, I have to look through my existing unordered list to see if the mouse is already there and if it just needs to be updated. In this case, it's not, so I'll add the mouse to the list. And then I go to put a light bulb in the list, and again, I have to look through my existing list to see if it's already got a light bulb. It doesn't, so we'll put the light bulb in the list. Okay, so the put operation may have to go through the entire list. Now let's think about the get operation. I want to get a lemon. Well, I can start at the beginning of the list and go through my list until I find the lemon and then return the associated value. So it looks like, again, we have to go all the way through the list. And as you might guess, when we want to remove an item, we have to start at the beginning of the list and go until we find the list, just like with the get operation. And if we wanted to remove the lemon, we would have to go until we find it and then remove it from our list. Okay, just to review the map operations with the unordered list, we had our three major operations, and the time complexity of the put was actually order n. So it will have to go through the entire list to see if an item is in the list and possibly update it. So we'll always have to go through the entire list. The get operation may get lucky and it may find the item right away, so it may finish in almost instantaneously, but in the worst case it will have to go through the entire list, so again it's also order n. And finally the remove operation, again we'll have to go through the entire list to see if the key is in the list, so again it's order n. It seems like we should be able to do a little bit better than order n for all operations. So let's try a different implementation. This time, instead of unordered, we'll try keeping things in order, so basically alphabetical order by their key. And let's try using an array instead of a list. Okay, so let's go ahead and start putting items in our array here. So this time we'll keep them in order by their name. So again, we can think of this as basically alphabetical order. So I'm going to go ahead and start off by inserting a baseball at index 0. And I'm also going to keep track of my first available index, so index 1. Okay, now I'm going to go ahead and insert a lemon. So I have to figure out where that belongs. So it belongs after the baseball, so B followed by L. Okay, gosh, let's go ahead and insert an orange now. So an orange, that comes, O comes after L. So we'll go ahead and insert that at the next available spot. Okay, so in order to figure out where I have to insert something, I do have to somehow go through my data and find the insertion point. And in the worst case, the insertion point would be the first available spot. So imagine that I want to insert a bear. Okay, so baseball, B-A, bear, B-E. Bear comes after baseball, but it's certainly before lemon. So I'm going to have to move everything over, starting at lemon, and insert the bear in. So in order to move everything over, I had to basically go through all of my remaining data. Okay, so you might already have some intuition about how the put operation is going to work. It may, in the worst case, have to move all of the items over. Okay, I'm going to go ahead and insert a few more items here. So I'm going to go ahead and insert a calendar. So the calendar comes after the bear. And now I'm going to insert a light bulb. So light bulb comes after lemon, but before orange. Now I'm going to go ahead and insert a mouse. So mouse comes after lemon, after light bulb, but before orange. Now I'm going to go ahead and insert a pencil, which comes after the orange. And now I'll insert an umbrella. Okay, so we've got a whole bunch of items inserted here. Okay, so let's talk a little bit about the get operation. So the get operation, if I wanted to get the lemon, I could do what I did with my unordered list and iterate through until I found the lemon. But we've actually already seen a technique that works much better here. We could actually do the binary search. So we could pick our middle item, and that would divide our list in half. So if lemon comes before light bulb, then I won't have to look at remaining items here. Then I could again recursively subdivide my list into half and half and half until eventually I pin down the lemon. So we've covered this earlier in the semester. Binary search is a log n operation, log base 2 of n. So it looks like my get operation could actually be considered to be log 2 of n. Okay, so let's talk a little bit about remove. In order to remove something, I have to find it first. So again, I should be able to find any item in log 2 of n. But once I find it, in order to be able to search this using binary search, if I remove an item, I actually have to fill in that empty hole, so I may have to move everything over. And in the worst case, I might be removing my first item and have to move all n items over. So although I might occasionally get lucky and be removing the last item and remove it in log n time, occasionally I will also get intermediate items and have order n time. So let's go ahead and talk about time complexities too. So the maps with the ordered array, again, we'll compare the operations and their time complexities, and we'll include the unordered list again just for the sake of comparison. So our put operation on the unordered list was an order n operation, and on the ordered array, again, we might have to shuffle everything in our array over. We may go through all n positions of our array, so it's also order n. The get operation, for our unordered list, in order to get something, we first had to find it, which may require us going all the way through the list. Although if we're lucky, we might find it really early on in the list and finish early. With our ordered array, though, we can do quite a bit better. We can use binary search, and we can find it in log n time. Our remove, however, for the unordered list, we had to find it first, which might require going through all n items. For the ordered array, we can probably find it pretty fast using binary search, but once we find it, we have to fill in that empty gap when we remove it. And if it's early on in the array, it's order n time. Okay, so basically what we find here is that both the put and the get don't perform very well. And if you remember, we talked about how these operations are somewhat array-like. We kind of think of the key almost like an index in an array. And one of the things we're able to do with arrays is we can put something in the array and get something out of the array in order one time. And we would really like to be able to do that here, to have fast access. And that observation actually tells us where we're going from here. So we've just attempted to use linked lists and arrays, and neither of them gave us very good time complexity, but using an array could give us the right time complexity if we use it in the right way. So we're going to talk about a technique of using the array where we can somehow convert our key to an index, which we weren't doing here. We were keeping things ordered, which isn't quite the same as converting the key to an index. So this process of converting a key to an index is referred to as hashing.